Okay, we're going to talk about Hess's law today, and I think most students actually kind of like this once they get the idea of what's going on. It's one of the things that the students told me last year kind of made sense to them. So hopefully this will make sense to you. You just have to understand why it works, and that's probably the hardest part here. Even if you don't understand why it works, you're probably going to be able to do the process. But I want you to understand why it works. So Hess's law. Has a lot to do with delta H being a state function. Okay, so I tried to make a big deal about that the last couple of days so that you can understand that it doesn't depend on the path that we take. It just depends on the initial H and the final H, and then we can figure out the change. Okay. Delta H is actually well known for a lot of reactions. There are a lot of reactions it's very simple to find this for, and we usually do that using the calorimetry. Okay, so the stuff we talked about yesterday, delta H equals, and actually it's usually written as Q equals C times M times delta T. But in a constant pressure situation like a coffee cup calorimeter, these two things are the same, Q and delta H. Okay. So we can find the delta H fairly easily for a lot of reactions. Now there are some reactions where it's not practical to do them in a coffee cup calorimeter or even a bomb calorimeter, and even some reactions that maybe we couldn't ever really get to happen in real life without other reactions happening along with it. And so it's hard to measure the delta H for every single reaction that we might be interested in as far as the energy change that would happen in that particular reaction. So we have sort of a workaround there where we can estimate the delta H using Hess's law and using the idea that it doesn't matter the path that you take. The only thing that really matters is your starting point and your ending point. Okay, so here's an example. We've got this CH4 gas and it's being combusted. Okay, and really you can think about this as sort of a two-step reaction. Or you can think of it as a one-step reaction, right? So if this all happens in one step, the way we typically think about this happening is the CH4 plus 2O2 goes to CO2 plus H2O down here, okay? That's the way we usually write our reactions. Now, you probably know that complete combustion does not usually occur, okay? A lot of it will be converted into CO2 and H2O, but then we're also going to have some carbon monoxide being converted here. And so what we can do here is we can actually, if we think about the energy change that happens when we go from CH4 to 2O2, making the carbon monoxide, and we know the energy change it takes to get from the carbon monoxide down to the carbon dioxide, then that's going to equal the same amount of energy that it gives off when it goes straight from the CH4 down to carbon dioxide. Okay, so it doesn't matter if we do this in a two-step process or if we do it in a one-step process. It's still going to end up being about the same, Okay, so the H2 here and the H3, if you add those two together, that's going to be the same as the H1 over here. So it doesn't matter if it happens in one step or two steps. The only thing that matters is getting from here to here. Okay, starting point and ending point. The in-between really doesn't matter that much, okay? So that's what Hess's law says. If the reaction's carried out in a series of steps, you can add up the delta H for the individual steps, and that's going to equal the delta H for the overall reaction. Okay, and this works because delta H is a state function, because again, it only depends on what you're starting with and what you end up with. All of the in-between doesn't really matter, okay? So we can actually think of this reaction as happening in two steps, and this is the way that this works if we're going to write it out, okay? So we've got our first reaction here would be the CH4, and I'm going to try to squeeze this in here, plus the 2O2 gives us CO, carbon monoxide, plus 2H2O, plus 1/2 O2. Okay, so that's our first step. And then our second step here is this reaction going from CO plus 2H2O plus 1/2 O2 to our final product here, CO2 plus 2H2O. Okay? And so if we add these two reactions together, I'm going to run out of room here. But here's what I'm going to end up with. You can actually, you can just add these reactions as though we had, equal signs here. So you can sort of think about this as almost an algebraic equation, okay, where you've got two sides to the equation. So we're just adding all of these together, all right? So we end up with, when we add it all together, CH4 plus 2O2 plus CO plus 2H2O plus 1/2 O2. And that's going to give us, on the other side of the equal sign, we're going to have CO plus 2H2O plus 1/2 O2 plus CO2 plus 2H2O. Okay? So that's when we add both of those equations together. All right? Now, just like in algebra, if you had x plus y equals 2x plus y, if you've got a y on both sides of the equation, these are going to cancel out. Okay? And then that's a bad example because 2x can't equal x. Well, I guess, no. That's a bad example. But you get the idea. If you have the same variable on both sides of the equation, then you can cancel it out, okay? And you can sort of think about these in thermodynamic functions. We can think about these things as variables, okay? And so we're essentially just writing the net equation, the overall equation here. You can also think of it as a net ionic, where you're canceling out things that are the same on both sides. All right, so we're going to start doing that. We've got 2H2O here, 2H2O here. We've got a carbon monoxide here, carbon monoxide here. We've got a 1/2 O2 here, a 1/2 O2 here. Okay? So when we've canceled out everything that we can on both sides of the equation and we add these things together, what we end up with is CH4 plus 2O2 gives us CO2 plus 2H2O. And so if you notice there, this was step 1, okay? And then we went down to here, that was step 2. When we added both of those reactions together, what they ended up giving us was here to here, okay? And so you can basically just add those things together, and when you do that, when you add the equations together, you also add together the delta H's, okay? So the delta H for this first equation up here, negative 607, okay? And then the delta H for the second equation here is negative 283. So when we add the equations together, we also add those delta H's together, and we end up with this delta H right here, negative 890 kilojoules. Okay? Hopefully that makes sense. So we're going to do some example problems here and see how this works. But there are some things you can do to manipulate these equations to make them work. Okay? First thing you can do to one of these chemical equations is you can flip it around. Okay? So you can flip it backwards. So that means that we would write in this first one here, we would write the product, CO2, as the reactant, and we would write the reactants as products. Okay? Now if we flip that around, just thinking about what that might do to the delta H, and we talked about this the other day very briefly. But if going this direction with the reaction number 1 here would give us negative 393.5 kilojoules, in other words, it's releasing that much heat. To go back this direction, it's going to have to absorb that same amount of heat. So the delta H would then be a positive. We'd have to change it to a plus 393.5. Okay? So that's one thing that you can do. Now, I'm not saying we want to do that on this one. Oops. There we go. Not saying we want to do that on this one necessarily, but you can do that. And then the other thing that you can do is you can multiply the entire equation by some number. Okay? So let's say that I wanted to multiply this whole thing by 2. So then I'd rewrite that as 2C plus 2O2 gives us 2CO2. And then when I do that, I have to also multiply my delta H by 2. Right, whatever I do to the equation, I have to change the delta H as well. So then that would be, you know, whatever that is times 2. I should be able to do this. Negative 787 kilojoules. I think that's right. Okay, so that's how that works. Again, for this particular problem, I don't know that you're going to have to multiply that one by 2. We'll have to take a look at it. But those are some of the things that you can do to manipulate these equations. And the goal here on these problems, they're going to ask you to calculate the delta H for a reaction. And they're going to give you the delta H for a couple of closely related reactions, okay? Which is what they're doing here. Now what you have to do is figure out how to rearrange equation 1 and equation 2 here so that when you add them together you end up getting equation 3, okay? And so it's like a little puzzle here to try and figure out how these work, okay? So the way I'm going to do this, I'm going to just sort of look at my goal here, number 3, look at what I need. And it looks like on the reactant side I need to have carbon and I need to have oxygen on the reactant side, okay? So as I'm looking at this thing, it looks like this first equation is okay as written, okay? Because I've got carbon on the reactant side, and that's the only, equation number 2 doesn't have any carbon, right? So the only place that's going to come from when I add these together is equation 1, and so I need to keep equation 1 basically the way that it is, okay? So I'm just going to rewrite equation 1 here. Gives me CO2. And so my delta H is going to stay the same here, negative 393.5. Now the second equation, if I look at this, the second equation has carbon monoxide on the reactant side. I need carbon monoxide to be on the product side in my final equation, okay? So this one right here, I probably need to flip so that the reactants become the products and the products become the reactants. So I'm going to rewrite this thing as CO2. This is equation 1, this is equation 2. CO2 yields CO plus 1/2 O2, okay? And now I've got to change the delta H for this one because I flipped the equation around. So this was negative, this delta H right here. Now it's going to be positive, okay, because I'm writing the equation backwards. So now it's 283.0 positive, okay? Now when I add these two equations together, it should give me equation number 3. Now let's see if that's right. My carbon dioxides are going to cancel out here. There's one of each on each side. And this 1/2 O2 over here is going to cancel half of my moles of O2, and then I'm going to end up with a 1/2 over here. Okay? So then when I rewrite this thing, now it's carbon plus 1/2 O2 gives me carbon monoxide, and that's the equation that we wanted. Okay? Now my delta H for this one, since I've added the equations together, I need to add together the delta H's as well. And when I do that, find my calculator here. Getting negative 110.5 kilojoules. Okay? So ultimately what they're asking you for, calculate the enthalpy of combustion. Okay? For this reaction. So our delta H is going to be negative 110.5 kilojoules. Okay? So the answer that you're looking for, you're always looking for the delta H number. Alright? You just add up the equations to figure out what you have to do to your delta H's before you add them together at the end. Okay, let's look at another one here, because I think you just need to do some examples of these to start to get it. So they want us to calculate the delta H for this reaction right here. And they're giving us these 3 reactions and their delta H's, okay? And so basically we need to figure out how are we going to rearrange these 3 equations down here so that when we add them together, they give us the equation up on the top that they're asking us about. Okay. So let's just start looking through these here. It looks like in my top equation, let's see, let's call this equation 1, equation 2, and equation 3, just to make it easy here. In equation 1, I've got C2H2 gas on the reactant side. And if I look up at the top equation here, the one I'm trying to get to, I need C2H2 gas to be on the product side. Okay? And so it looks to me like this one maybe needs to be flipped, because that's the only place I see C2H2 in any of these equations. The only place that's going to come from is from reaction 1, and so it needs to be on the product side. Okay? So we're going to flip this first one around and rewrite it as, this is equation 1, CO2 plus, I'm going to be a little lazy with my states of matter here, gives us C2H2 plus 5 halves O2. Okay? And I got to keep track of my delta H's here. I flipped this thing around, so my delta H is now positive 1299.6. Alright, now equation 2, if I'm looking at that one, that's the only one that has just solid carbon in it. Okay? And that looks good. That's on the reactant side up here in the equation that we want. It's also on the reactant side, but the problem there is there's 2 moles of carbon in the final equation, and there's only 1 mole in my equation number 2 here. So what I'm going to do on the second one, I need to multiply this entire equation by 2. Okay? So I'm going to end up with 2 carbons plus 2 O2. And that's going to give me 2 CO2. Okay? And my delta H for that second one, because I multiplied the equation by 2, delta H is a extensive property. That means you increase the number of moles that you're burning, you're going to increase the heat. So this is now going to be negative 787. So I guess I was right. I did it in my head before. So negative 787, it's the delta H on that one. Okay? And then the third one here, well, the third one looks okay the way that it is, I think, because we've got H2. That's the only place that we have H2, and we need 1 mole of that in on our reactant side for our final equation, so I think that looks okay. Alright, so I'm just going to rewrite that one the way that it is. H2 plus 1 half O2 gives me H2. And so because I didn't change anything on that one, the delta H is going to stay the same, negative 285.8 kilojoules. Now I'm just going to add all 3 of these equations together. It's not a straight line. And do some canceling where I can. Okay? There's 2 CO2s on the reactant side on equation 1, 2 CO2s on the product side on equation 2, so those cancel out. What else do I have that cancels out here? It looks like the H2Os cancel out in equation 1 and equation 3. And then we've got some oxygens that cancel out. Okay, it looks like 5 halves, which is 2.5. Okay, so we've got 2 oxygens that cancel, 2 of these oxygens, and that leaves us with 1 half over here. And then that 1 half on equation 3 will cancel the other 1 half. Alright? So if we had added all of these together, we would have ended up with 2.5 moles of oxygen on the reactant side and 2.5 moles on the product side, and then those would have canceled out. Okay, I'm just trying to do it without having to rewrite the whole thing. So then, what we end up with here, our final equation, 2C plus H2 gives us C2H2. And that's exactly what we wanted on this one. So then we just have to add up our delta H's here. See what our final answer ends up being. Whoops. Sorry. You probably already figured this out already. Getting 226.8 kilojoules. So this ends up being a positive delta H, which we could think about this at the end. This is actually an endothermic reaction, okay? Because it's a positive delta H, we're going to have to supply some energy, supply some heat to this thing in order for it to actually occur. Okay, and then the last example here, again, just to give you even a little bit more practice. So they're giving us the equation for graphite burning, and they're giving us the equation for diamond burning. It seems a little weird, but that's what's happening there, the combustion of each of those things, okay? And they're not very different, is the crazy thing. So burning graphite, burning diamond, you can actually use those two equations to figure out the delta H for converting graphite into diamond, okay? So if we're looking at what we ultimately need, this is our final equation that we need here, okay? These are our two equations with delta H's that we know. And so then we just have to rearrange these. In this one, it's not that difficult to see what we have to do here. Equation 1 is written fine the way that it is. Equation 2, the diamond needs to be on the product side, so we need to flip that one. Okay, so I'm going to rewrite equation 1 here. I'm going to abbreviate a little bit. And then equation 2, I'm going to flip it so that the CO2 is on the reactant side. And then the diamond plus O2. And then because I flipped it, my delta H, the sign needs to be changed, so it's now a positive 395.4. These are both kilojoules. Okay, so then when I add these two together, CO2's cancel out, the oxygens cancel out, and I'm left with graphite going to diamond. And my delta H for that reaction, kind of surprising here. We get a 393.5 plus 395.4. So that's 1.9 kilojoules. So it takes 1.9 kilojoules of energy in order to get graphite to turn into diamond. Obviously, it's a little more complicated than just supplying it with energy. Otherwise, that would be a very easy thing to do. It also has to be restructured. So, but that's the amount of energy that it takes, theoretically, to change graphite into diamond, based on the thermodynamic data. Okay? Alright, so that's Hess's law. Hopefully that makes sense. Again, it's just kind of an algebraic process here, and I think once you've practiced a few of these, it's going to make a lot of sense to you. And there's not a ton of thinking involved with these. If they give you an equation, and they want to know the delta H for it, and then they give you several other equations that have delta H data, that's your big hint that you're probably going to do Hess's law on that particular problem. Okay? They're usually fairly easy to spot. So that's that. I guess we'll see you next time. I won't see you. You won't see me either, so, well, you know what I mean.